here's what happened. I was doing projection pursuit, and I got this rate of algorithm, et cetera, and then Andrew showed me that this can be applied very easy to neural nets, and we can really do something with this. So I included it in my paper, the application, and basically it involved dealing with a target function which is in a convex hull. But I was moving in another direction because I had read the papers by Vapnik about the kernels. This is 30 years ago. And Vapnik was claiming that the new direction should be in local learning. We should focus only on learning for one query because these other methods might fit well on average or with high probability, but what if you're in that small probability set that's trying to decide from all the data what treatment you should take or what the diagnosis is? So I decided that's a good idea. I think I'll stick with that. So for a while. But then Andrew came along with these applications, and I said, well, that's not so bad, because my thoughts about neural nets in 1990 were multiple layers, and I just had no idea how to interpret that. So I still don't, to be honest with you. I'm sorry. And I guess I'm too old. I'm kind of think that these things are just going crazy when AI is going to take over our lives, and we're not going to really know what's happening. We don't need to. We'll let him do everything. Well, in this particular case, I'm interested in learning at one point, and I'm going to call that 0. I can look at my data that way by subtracting off my query point. And I'm going to go back to looking at it the way I learned to look at it from your father, Tom Cover, who wrote one of the first papers on this. And
I'll tell a little story on that. So neural nets came from my birth dad, Roger.
Yes, really bad.
But I didn't tell Tom about my interest in neural nets, and I hadn't until like second or third year with him read that his thesis was also about neural nets. Yeah. So then, yes, I benefited from both fathers.
Yeah. And Tom was one of the first people that I looked around for to do dissertation when I was a part-time student at Stanford working at Lockheed. I was looking for applied math to do. And he was a young assistant professor, and and he was telling me about his work with Hart, and I was fascinated by neural net, by the nearest neighbor. Really fascinated. But I guess I never got to him for a thesis. I tried Danzig. I couldn't solve the traveling salesman problem, so I gave up. And then I tried Professor Levine in fluids, but I had done fluids as an undergraduate, and that was boring. So then I went to Samuel Carlin. I said, I'm really interested in game theory. And he said, I don't do game theory anymore. Go to Professor John at Stanford. Then I went to Professor John, and somehow I took real analysis, and I ended up doing ergodic theory, totally theoretical stuff, losing my scholarship at Lockheed and having to be a TA at Stanford for about 1/3 the salary. And then it took me a long time to get back to applications. So, why local learning is so important? Well, first of all, what I'd like to do with local learning is I'd like to look at high-dimensional problems and then go down to a lower dimensional projection and use some of the methods, but I have to understand how to do the methods in moderate dimensions. And that seems to be pretty difficult even in 2 dimensions or 3 dimensions. So we'll start off with this problem. Another thing I'm interested in if I can get a low dimension after going through all of these things, most of which details I'll just omit, just go through you, just sort of motivational. If I get a reasonably low dimension, and if in this sphere, in this reasonably low dimension, the function's approximately linear, I've got some interpretability. So if I know I can get an accurate estimate with a high dimensional problem in, say, 3 dimensions, if I can get to that somehow, get to that situation somehow, then I know those 3, usually they're 3 coordinates. I'll probably look at subspaces, which are just subsets of the coordinates. Then I know, if it's an accurate estimate, I know that I've got some interpretation there. But also, if it's a single hidden layer neural network, there's no reason why you can't do exactly the same thing after you've trained, but then you have the problem of, well, did the query point miss that set? But so I was still pleased with what Andrew did, right? So it's not that I left and didn't work in that area. It's just I ended up going in a different area. But I got virtually nowhere at first until I published a paper in 2009 in the I.P.A. And I moved into other areas. I was doing transportation and some other things, some other statistics too. But in transportation, after about 15 years, I found that they already had a result very similar to the result that motivated Andrew to use greedy methods to get these neural networks trained. And that was by a result in the 50s by, let's see, Frank Wolf had an algorithm for minimizing a convex function on the convex hull of finitely many vectors. So this is kind of like the dictionary of the extreme points, and we take the convex hull in this case, and then we minimize a convex function. And they used an algorithm which is a relaxed, greedy algorithm, essentially just like we do, Andrew's used with neural nets and how I did in my paper on projection pursuit. And that culminated in a paper, just, I don't know if it's published, I got it when it was archived, by Bartlett and Yee on approximate and stochastic greedy optimization, which shows that the 2 ideas, one in approximation theory in a neural net training, and one, the Frank Wolf algorithm in optimization, are equivalent. However, it depends on differentiability assumptions, which we don't need in the neural net case or the projection pursuit case or the approximation case. But fortunately, I can get around some of that to do what I'm doing here. But I conjecture that their algorithm will not require any differentiability. The greedy algorithm will go in rate 1 over k, where k is the number of iterations. Okay, so here I was with a result in 2009 that I was stuck with, and I only recently figured out maybe where I can go with it. And not that I've gone a great distance, but hopefully I can get some younger folks to maybe get some influence from what I'm suggesting and either develop it or come back and say that it's garbage. Either one will be acceptable. So I'm going to give 2 bounds here. So again, there are my query is 0, and those other dots up there. Let's see. Does this work? Yeah. Oh, you hold it. These are the data points, and I'm going to call it K nearest neighbor regression. And I label a few things like radius is here, and this is the sphere. Supposedly it's in D dimensions, but I can only see in 2 or maybe 3. Usually I see well in 2. And there's the kth point there on the boundary. And I'm going to use a simple, smooth, a simple linear combination of the responses. And let's assume, although they could be random outcomes, the x's. Let's assume that they're fixed controls, and this is the data set I have. And I'm going to deal with it as if I don't know the yj's, which are the responses, and see what I can get in terms of getting an estimate. Well, there was already some results on this, and one is in the book by Loader, Clive Loader, published in '99, in which he actually looked seriously at the local learning problem, but in more moderate dimensions in terms of applications. Vapnik had wanted us to go into higher dimensions, and so what I'm going to try to do is project down and use these results. And that will come quickly once I get through. So here's...
Is this a bound on a mean squared error of the case?
For given weights here, this is a bound on the mean squared error of this estimate. Now, Loader assumes a fixed variance. I'm assuming just a bounded variance in my bound, which I actually did this with correlated noise, but let's say these results here all assume independence. So this is a diagonal matrix, and it's a bound on the actual noise. So each noise, the ith noise is bounded in expectation, squared expectation, by the ith diagonal element of sigma naught. Turns out in his bound that he has in here, so one thing we're doing here is we're looking at, we're assuming that in this spherical region, we're close to a linear function. But we're exactly equal to the linear function at 0, but otherwise we're close to a linear function. And he uses an error of actually an affine function to be exact, which is epsilon p minus 1. So this is kind of, if you look at this formula, this is kind of what you get in the Taylor remainder formula. And the solution he gives requires higher moments to be 0 with respect to the data points in order to get this bound. And he doesn't have a bound. He assumes the regression function could be unbounded here, not unbounded, but he doesn't have a bound on the regression function. But you have these constraints, and it turns out even for p equals 0, this is not the best bound. And when you do the minimax solution, you don't get the right minimax solution. But I won't go into the details for that. What I did here in this, in my bound was, well, I was using the fact that I'm going to stop, a certain distance away or a certain number of neighbors. And I'm going to assume that I know something about my regression function within that. It might be close to linear, but it isn't exactly linear. It could have wiggles in it, but I'll assume that the variation is bounded. So now the variation being bounded gives me a chance to get a minimax solution here. And again, I'll just show you the formula. If you assume and we do optimization over W, so you've got these bounds, and if you do this optimization just assuming that you can't know the variance exactly as this bound, but you just assume the bound, you basically got a bias term here. This is your bias term, and this is your variance term. And all you can really do is you can't really control this, so you just keep that and you focus on the bias term. And you'll notice in both, and this is also true with Loader's bound, that this doesn't depend at all on the y's. Now that's important for a couple of reasons. First of all, and let me say why it's important even for moderately low dimensions. In moderately low dimensions, the method, the use, this particular approach to local learning, there are kind of two approaches that people have done in the literature, in even small dimensions. One is, we want to know how many neighbors to take or how far to go out, where do we go, how much data, we use all the data or whatever. So one of the approaches, there's two approaches. One is I'll take about the more sophisticated one, is the plug-in estimate. That's where you develop a bound by plugging in an estimate that's more complicated than something simple like this. Namely, usually a kernel or a truncation. You put in a kernel, a rectangular kernel with an unknown bandwidth. And when you do that, you get a bound and you can optimize it. Bias variance trade-off. But there's two problems with it. One is that admitted by the in the literature, I'm not an expert in those techniques. And that is that because you put a plug-in estimator, it's not a simple affine combination of the data. The result is that these bias terms depend on the actual YJs. Because it doesn't come out this simple. And when it depends on the YJs, there's some problem in the optimization in getting the right, say, kernel bandwidth. Another problem with that is, admittedly, they're admitting to some problems, but now let's suppose that we're going to try to take this kind of analysis and look for, say, in a 100-dimensional space, or in even a 10-dimensional space, and look for a subspace, low-dimensional subspace, and apply these techniques by doing what? Well, we can take advantage of the fact that this doesn't depend on the regressors. So we can do all the computation we want forever and ever and ever, and we're not going to ruin things. The trouble is, if we get to use some of these other methods, which only have a slight effect, and asymptotically it's negligible, but if you're doing it 100,000 times, the errors may add up. So the other method, which I never liked, was that, okay, we want to determine R or K, either one, and may get different results. What do? Well, we do this everywhere with all our data in the complete data set. We pick an R, and we look at every point as a query, leave it out. It's called cross-validation. Go out distance R, do our algorithm everywhere, get an average performance, and then do it again with another point as query point, leave it out. And of course, we can all do that because we can compute fast. And obviously, this, if you think about it, this isn't maybe such a good idea, because what's happening over here may not be happening over here at a data point that isn't even in there. And things may look different, scale, obviously, yeah. And that's admitted to in the literature. So with that, I guess I'll finish the first page and go through things rapidly, because I probably have I do, okay. So that means I got to go forward fast. And this is going to contain all the math, by the way. So even if you reject my submission to this meeting, I can send you the slides. There are some theorems in here. Most of them. One thing at the end is a secret, so I'll leave that to the end. So we can also do this with classification, by the way. So in classification, we get those bounds a little bit more complicated. So now the functions between 0 and 1. So that's a little bit different than just be bounded variance, bounded variation, because bounded variation could differ by a constant. So that's a slight difference. And so, also, even the previous bounds, we could change these powers, by the way, here in the kappa. Kappa is within, this function is within kappa norm x squared. It could be kappa norm x to the alpha, where alpha is greater or equal to 1. Can actually achieve, in the previous one, I can achieve the same bound. I don't think I could in this, and this is actually best possible if I'm willing to take the worst case sigma naught. Now, in this case, the sigma naught is actually related to the data, because the sigma naught in this case is going to be what? It's to be the probability. This F will be the probability that, say, it's a success. So the variance at any observation point at x is going to be f times 1 minus f, the variance of that. And so there is a connection, but again, we're just putting in the worst case. So if we have an upper bound on success probability, or we have an interval of a success probability, we could put in a bound, and we're basically concentrating on these other things. And by the way, these can be done. These things, we can get these minimax, or as you'll see later, quasi-minimax or pseudo-minimax results by doing greedy, relaxed learning of the minimum of a function using the algorithm of, using algorithms of Yee and Bartlett. Now, I can only do it here if I can generalize their theorem. I've been trying the last couple of days. I may not succeed. Maybe somebody else will. Without this differentiability assumption, this greedy algorithm. Otherwise, I can't use it here. But I can use it in what I'm going to do now. So what I'm going to do now is I'm going to go back to the other one and say, well, so we want to maybe and extend this and try to do what? We want to find out what K to pick, what R to pick, or whatever. And we're going to try to do it a different way. And by the way, if it's a classification problem, some of you may think, well, why aren't you using logistic regression? Well, immediately the problem, the bounds you're going to get are going to depend on the observations. Because in the logistic regression, you have to look at the variance of the sigmoidal, e to the linear divided by 1 plus e to the linear. You got to look at the variance of that, and that's going to, unfortunately, it's going to contain, because of the nonlinearity, et cetera. It's going to, again, what the influence of the data is, I don't know, but if you're going to be using this over and over again to search for something, you have to be careful. So what I'm doing is I'm basically assuming linear functions inside the sphere here when I'm trying to solve the classification problem. But we can do those now because we have Karmakar's algorithm, and we even have something stronger called cone programming, where we can put in certain constraints and solve problems rapidly as if it was like on a calculator multiplying and dividing 50 years ago. So here's the binary classification bound. You can start forgetting that. The point I want to make now is let's look at the data. So I don't actually know how to proceed with my original bounds and make this ball bigger. I have some problems extending these bounds because if I'm going to assume, I'm assuming that my function is approximately linear in the entire sphere. I don't know how to do that problem when I don't have data out there. Well, and look at what happens to the data, and this is especially going to be true in higher dimensions. The data is all pushed into some small area there. How can I solve a problem where I don't know what's going on there? I have no, well, why don't we forget about that? Let's just look in here. Well, convex hull. Look at the convex hull. And let's go quick now. So here the problem is, let's get error bounds using the convex hull. So, and actually, let's just look at this place here, and let's do these bounds over again. So that's what I'm doing here. And now I can't solve the minimax exactly, but I can get good tight bounds. And I welcome you to read some of these things. And it goes pretty fast. And I finally talk about computing, and finally I get a bunch of bounds on the bounds that I've derived by working on the convex set instead of working on the sphere. Now, before I go further, I'll say quickly, do I have that now? Yeah. Let's look at the exact linear case for now. Those slides were assuming I was approximately linear. In that case, we can solve this with linear programming. At least we can evaluate the bounds because this is our objective function to go through the algebra writing it all out. And this is your bound on this expectation if the function f is linear. And so to minimize this thing, actually you have to, first of all, you have to maximize that, then minimize it. Because this is the worst. To get the bound, you need the worst case with these coefficients in the affine function. That you can do with two linear programs. And another thing that we have to do now, because these convex sets are going to get thin, we have to have a bound on the gradient, in this case, of a linear function, or any true function, because it may be too thin. And so we bound that by a number that's adequate. And we have these two linear programs. And once we do that, we now minimize over the weights using relaxed greedy convex optimization to obtain the actual minimum. In this case, that's for the true linear case. Now, that we can do because we don't have differentiability here, but those corners in this linear programming problem, maximization problem, those corners, they can be rounded off because of this constraint. That's not a problem. So we can essentially assume the hypotheses of Yang and E. It may depend on going out at many places. So we can, although I believe that you can generalize that result. Now, armed with that thing, we can try to solve the linear problem and go to a point when we're done. And then we can apply these bounds and evaluate what we're doing. So now we get to the end. So I'll go to the next step. So we're now doing everything on convex sets. And this will tell you how to do it. But the results on the convex sets, I used any function epsilon of x that is 0 at 0 and otherwise non-zero, instead of kappa times a norm. That's important for a lot of reasons. We may not want epsilon to go to 0. We may only want epsilon 0 to be 0 and otherwise not because of sensitivity. So what I'm doing here is what I'm doing here in this general is I'm doing things on this convex set. I've got a multiple of a given function epsilon star, and then I'm multiplying it by the right multiple, and then I'm trying to figure out how does kappa behave. If I can estimate kappa, I can put it in and finish. And that's exactly what I've done with a resampling technique here. And I won't show the final things because it's also confidential with the client, so it's good that I'm stopping here. Yeah.
Thank you, Lee.
Yeah. You have a question, right?
Any questions? So let me summarize my understanding. This is tricky business because, all right, so the variance is that involves the sums of the WI squareds, right? If you equally weighted, and they were 1 over k's, that's a 1 over k. That's like that's like saying your variance is like 1 over the number of observations that you're averaging.
Yeah.
And you get more observations if you grow the radius.
Yes.
But now your approximation error gets worse as you grow the radius. Right. And this is the classical dilemma associated with local smoothing techniques. Yeah. When you work out the best trade-offs in typical function classes, they're terrible in high dimensions. Yeah. So to rescue what you're doing, you made two important comments. One was that you are considering the possibility that there is a lower dimensional manifold. Yeah. And the other is this idea to use the convex hull of those K points.
Yeah, that's the main.
And those are good ideas worthy of further exploration.
I didn't cover the other ideas, but I covered the convexity. That's the main first point, is to get away from Taylor's theorem. We think in Taylor's theorem we only have to think of spheres. We should forget that and start looking at convex hulls.
Okay, thank you, Lee. Let's take him again.
Let me give this thing away.